Okay, here's an example of IF4, our Lewis structure. I've written all of our rules off to the side here. I don't know, a lot of people didn't really follow the steps and had some trouble as a result, so we'll just go through them one by one. First, we write the skeleton structure, so IF4. Then we need to count our electrons. In this case, I brings 7, and fluorine, based on where it is in the periodic table, each brings 7. And we have a plus charge, so we need to subtract an electron there, so -1. That gives us 28 plus 6 is 34 valence electrons in this structure. Then we just sort of keep track after every step, so we've already used 8 for our skeleton. That leaves us with 26 valence electrons, or 26 electrons left to deposit. Now we get octets on the terminal atoms. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Again, adding 6 electrons, 3 lone pairs to each to get them each to an octet. We've used up 24 electrons, and now we still have 2 electrons left over. If we look at the central atom, it has an octet, 2, 4, 6, 8 electrons around it, but there are still 2 electrons left over, so we have to, at this point, put those electrons, extra electrons, on the central atom. Again, we're in the 3rd period. Iodine is way down the periodic table, so it's okay. And that's where those last remaining 2 electrons go. Now we've used all of our electrons. There's no electrons left over. At this point, you should check your work. On the exam, you'll have 2 hours, even though the exam should only take an hour. So yeah, definitely check that you have the correct answer, right? You can easily check that your octets, check the number of electrons for every single Lewis structure, and make sure you have them correct. So we'll check octets, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, terminal octets. Central octet, well, we're breaking the octet rule here, but again, 2, 4, 6, 8, 10 electrons on the central iodine, which is okay because we had those leftover electrons. And again, the total number of electrons in our structure, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34. We've used all of our electrons. We've got everyone to an octet, or as best we can, so we know our structure has to be correct. Next, we get to formal charge for this structure. So again, if you forgot formal charge, that's the valence electrons that each atom brought minus the electrons in the circle when we sort of think about each atom and think about sort of drawing that circle which assigns the electrons to each individual atom. So if I start with my fluorine over here, I can sort of think about that circle. I would say it brought 7 electrons. That was the valence electrons that it brought, minus, and electrons in the circle is 2, 4, 6, and then each bond that I sort of circle counts, 50-50, half for the fluorine, half for the iodine. So this counts as 1 electron as well. So 7 minus 7 is equal to 0. And it's the same for each of the fluorines because they're all 3 bonds, 3 lone pairs in 1 bond. Now the central iodine, I'll draw that circle. Ooh. That central iodine brought 7 electrons, but it only has 6. So 7 minus 1, 2, 3, 4 bonds plus a lone pair is 6, gives me a plus formal charge on that iodine. And again, remember the key rule at the end. Another way to check your answer here is that the formal charge adds to your overall charge. And so again, another check that you have the right structure is just check those formal charges. I have a +1 formal charge on iodine. I know my overall, not molecule, but my overall ion has to have a +1 charge. So this checks out that the formal charge does add up. Another check that I have the correct Lewis structure. Okay, B was one of these sort of skeleton structures. People did pretty well at this one. Again, C H3, nitrogen, put the 2 hydrogens on the nitrogen, just sort of drawing that skeleton structure out there. Now I need to sort of fill in lone pairs and things like that. My nitrogen has 6 electrons around it, and it's going to need a lone pair there to get to a complete octet. At this point, for these skeleton structures, the best way to check things is with formal charge. So again, almost always on these, the formal charge should be 0 on every atom, and we can check that we have the right number of electrons in the structure by checking the formal charges, or just by, for this small molecule, counting them up. I guess I'll do both. We have octets around the carbon, octets around the nitrogen. Each hydrogen has a duet, so that's good. We've done our sort of octet check. The total number of electrons in our structure, we'll just add all of that up. 2, 4, 6, 8, 10, 12, 14. And we were hoping to have 4 plus 5 plus 5 is equal to 14. So it does actually check out. Formal charges, again, check those as well. Each carbon brought 4 electrons. It's making 4 bonds. That's sort of the usual case for carbon. Brought 4 valence electrons, has 4 bonds, so it has a 0 overall formal charge. Each nitrogen, the nitrogen over here as well, brought 5 electrons, and it has 1, 2, 3 bonds plus the lone pair. So 5 minus 5 is equal to 0 on the nitrogen as well. This second one, again, was sort of a little perplexing to me. Remember, for this sort of table, really almost everything you can write down literally just by knowing the steric number. So 9 out of these 12 boxes are just calculating the steric number and knowing the basic properties of each steric number according to VSEPR theory. So for a steric number of 2, you form 2 hybrid orbitals, that's sp. The electron geometry then is linear, because that's the best way to arrange 2 things. And the bond angle for linear is just 180. For 3 things, sp2 hybrids, and the electron geometry is going to be trigonal planar. That's the best way to arrange 3 things in space. The bond angles are a circle divided in 3, which is 120. For sp3, that's our steric number of 4, that's tetrahedral, happens to be the best way to arrange 4 things in space. The bond angles then, that magic tetrahedral angle of 109 degrees. For 5, we've run out of p orbitals, so now we start using d orbitals, sp3d. This is a trigonal bipyramidal basic geometry, and in that sort of structure, in 3D, that has 90 and 120 degree bond angles. Again, you can take a look at the 3D shape there for trigonal bipyramidal. You have sort of the plane, 3 things in the plane, and then 1 up and 1 down for trigonal bipyramidal. Then for 6, we have the listed sp3d2 octahedral, 90 degrees. So again, you sort of just need to have this basic thing memorized. It's really not that many things to memorize. Most of them are pretty sort of straightforward. Tetrahedral is a little bit odd, trigonal bipyramidal, octahedral, but if you just sort of have this etched in your brain, you'll get almost all these right off the bat. So we'll go through and apply them. NH2O, the steric number here is 3, 2 bonded atoms plus a lone pair. Steric number of 3 means we're in this area of the table. That means we're going to have a trigonal planar electron pair arrangements. We're going to have bond angles of about 120 degrees. And our central atom hybridization is sp2. Now, again, when we start with that trigonal planar basic geometry, we have our N and H, the double bond O, and one of those 3 things is our lone pair. So the overall molecular shape here is bent because one of our 3 things is a lone pair, so all we see is that sort of bent shape. Okay, on to the next one. For POH3 here, we have a steric number of 4. 4 bonded atoms, no lone pairs. The electron pair arrangement is thus tetrahedral. The bond angle is therefore 109, that magic tetrahedral angle. The hybridization is sp3. The molecular shape then is going to be, since there's no lone pairs on the central atom, exactly the same as the electron pair arrangement. It's going to look, again, I'm not going to draw out the tetrahedron. It's a little bit hard to draw. But again, when there's no lone pairs, the electron pair arrangement and the molecular shape are exactly the same. So this is also tetrahedral. Okay, for our last one, we now have 1, 2, 3, 4 bonded atoms plus a lone pair, so a steric number of 5. That makes the electron pair arrangement trigonal bipyramidal. The bond angles then are going to be, in theory, 90 and 120. We should check that once we get the actual molecular shape, because sometimes for these large ones, the bond angles, like we lose some of these bond angles if we have enough lone pairs around the central atom. But we'll start with 90 and 120 and then just double check that that actually checks out here. The central atom hybridization is sp3d. And again, now the molecular shape here, it's this trigonal bipyramidal overall structure. One of those positions is occupied by a lone pair. So I'll put a lone pair somewhere over here, like that. Now, the resulting shape here, again, knowing the name of it can be a little bit tough. But again, if you think about taking this and turning it on its side, you'd get a nice sort of seesaw type geometry here, turning it on its side. So this is our seesaw shape. And the bond angles are indeed 90 and 120. There's a 120-degree bond angle here, and then these bond angles to the up and down positions are 90. If we added an extra lone pair, we would lose the 120 because we'd be down to just a T shape. Okay, I've got the rules for our resonance informal charge example down here. 3 possible Lewis structures of SCN minus. Let's start by doing our Lewis structure. Again, we've got the rules for doing that. If you didn't watch the first one, again, maybe go watch that one if you were having trouble with the actual Lewis structures. It's SCN minus, so 6 plus 4 plus 5 plus a negative charge, so plus an extra electron, gives us a total of 16 total electrons in there. Then my skeleton structure has used 4 of them. So I have 12 electrons left. Then again, I'll start with the middle structure. I'll put octets on the terminal atoms. 2, 4, 6, 8, 10, 12. And now I'm all out of electrons. So I have 0 electrons left over. That means that I'm now going to need to form those multiple bonds to get my central atom up to a full octet. So my central carbon only has 4 electrons around it. I need 8, so I'm going to need to take 2 lone pairs and turn them into double bonds. So for this middle one, maybe I'll arbitrarily pick 1 from each atom, take those and form them into a double bond. So again, I'll remove those lone pairs, double bond, double bond. Again, I'm not changing the total number of electrons in my structure. I've still used 16 electrons, but since I ran out, I now know that I needed those double bonds there. Okay, my other 2 Lewis structures, though, are just going to be that same structure, but I'm just going to take my double bonds, make my extra bonds in different places. So if I took both of my lone pairs from the nitrogen atom, I would get a triple bond here. And if I took both of my lone pairs from my sulfur atom, I would get this structure right here. And so yeah, the standard way of doing these Lewis structures does really help you for these two, because you can just sort of see, okay, I can take 2 double bonds here, 1 each, or 2 double bonds over here, and get all 3 Lewis structures really quickly. Okay, now we have to do formal charges on each atom. Again, remember, it's the valence electrons minus the electrons in the circle. If we think about drawing that circle around each atom, that's how we sort of assign an electron to each atom for the purpose of this procedure. So for sulfur here, it brought 6. And then in the circle is 1, 2, 3, 4, 5. So I have a plus formal charge on sulfur here. That central carbon atom, you should sort of be getting used to carbon almost always has a formal charge of 0. That's because it usually brings in, and it always brings 4 electrons, and it's almost always making 4 bonds, 1, 2, 3, 4. So that has a formal charge of 0. We don't need to write anything there. And then for nitrogen, it brought 5. And if I look at this structure, it has 1, 2, 3, 4, 5, 6, and the 1 bond. So it has 7 here. So this is a 2- formal charge on nitrogen. Okay, for the other ones, sulfur here gets assigned 6 electrons. These lone pair electrons plus the 2 bonds. So that's a formal charge of 0. The nitrogen here brought 5, but if I draw my circle, I would put 6 electrons in there. The 4 from the lone pairs and then the 2 from the bonds. So that's going to be 5 minus 6 for a negative formal charge on nitrogen. Then over here, again, sulfur brought 6, and here I'm going to put 7 electrons in that circle. So that's going to be a minus formal charge on sulfur. If I look at nitrogen, it here brought 5, and then in the circle is 5. Again, each bond I cross counts as 1, and the lone pair counts, for just both 2 electrons there. And the carbons are still 4 bonds, so the carbons are all 0 here. Okay, now that I have these, I can double check my Lewis structures one more time. Remember, the formal charges always need to add to the overall charge, so I can double check. +1 plus -2 is -1. -1, -1. Again, just another check that we have good Lewis structures here. Really no excuse to have a Lewis structure that's not following all the rules on any of these problems. Okay, then which resonance structure contributes the most to the structure of the molecule? Well, we apply our rules. All formal charge 0 is best. We can't do that, but smaller formal charge is better. + or -1 better than + or -2. So rule number 2 immediately rules out structure number 1 because it has that -2 formal charge. So we'll say structure number 1 contributes the least because of rule number 2. The smaller the formal charge, the better. Then the last rule here is, again, if I have equal formal charges, like here, 2 and 3, both only have 1 minus formal charge. So they're both pretty good Lewis structures, both pretty good at following these formal charge rules, but I'd prefer to put the negative formal charge on the more electronegative atom. If you look on your quiz, you have the electronegativities on the back of the quiz, because again, it can be hard to determine what the the difference in electronegativity here. Nitrogen is 3.0, sulfur is 2.5. And so it turns out nitrogen is more electronegative. That means that it's going to pull the electrons more toward itself, so it's sort of more stable having that negative charge compared to the sulfur. So that makes structure 2 with the negative formal charge on nitrogen the better and therefore the best overall structure. Our last valence bond theory question looks at counting the sigma and pi bonds, so pi bonds in the following molecule. Given that each double bond contains 1 pi bond and each triple bond takes 2 pi bonds, we have a total of 5 pi bonds in this molecule. For hybridization, we need to fill in our lone pairs. For this nitrogen over here, we can see that it currently only has 6 electrons around it. It will have 1 more lone pair of electrons to get to a formal charge of 0 and an octet. Then over here on this side of the molecule, our other nitrogen, we'll also need a single lone pair over here to get to an octet. From that, we can get the steric number of each. On the left, we have a steric number of 3, which makes it sp2 hybridization to make 1 plus 2p equals 3 hybrid orbitals. Over on the right, technically we wouldn't have to hybridize this atom since it is a terminal atom, but if we did, we would use its steric number of 2. 1 bonded atom plus 1 lone pair would give us sp hybridization.